title is Visual Intuition and the Ancient Sky. My subtitle, Complexity Theory and Plasma Cosmology. I'm going to beg the graces of those who know more about complexity theory and cellular automata than I do, and they will help us through this, the most difficult part of my presentation. This is the defining image, the squatter man. We've seen him before, we'll see him again. These are more familiar images to you already. The squatter man in petroglyphs. This is Kayenta, a defining image that will come up later. We go all around the world and more in Arizona. So you see how global, and this is hard to see, but it's in the state we're in. If anyone knows who drew this, I'd be deeply appreciative. I came across it through Peratt Images on Google, which led me to ancientdestructions.com. We see here, marvelously, we see here Stone Age man and woman gazing at squatter man configuration in the sky after having made a petroglyph about it. Likewise, what is above it in the polar configuration after having made another petroglyph of it. So, I'm going to tantalize you with something very strange. This will be the subject of my exposition of the work of Stephen Wolfram, author of A New Kind of Science, 2002. And it's very strange, isn't it? I will go over it later, but I just want you to look at this image, particularly at this. Just hold that image. My thesis. Complexity theory is a powerful natural ally to plasma cosmology. Both tell us that in reconstructing the sequence of events in the ancient sky, we have to imagine watching images unfold in a sequence, a story. The events and images are often too complex to be predictable. Both tell us that visual intuition will be an indispensable guide and even, in many cases, a form of proof. We'll see if I make this thesis clear to you or not. Galileo looking rather feisty, don't you think? Now, Mel Atchison gave us the popular version of Galileo's famous statement. The book of nature is written in mathematics. Since that simplification, which we are more familiar with than the original, is not really the whole of what Galileo said in one splendid long sentence of Italian prose, I'll read you a translation of that sentence. Nature does not appear in it, but philosophy and the universe do. Philosophy is written in that great book which ever is before our eyes. I mean the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. The book is written in mathematical language, and the symbols are triangles, circles, and other geometrical figures, without whose help it is impossible to comprehend a single word of it, without which one wanders in vain through a dark labyrinth. 1623, Il Saggiatore, the Essayer. Now, my theme will be partly the mathematics bashing, which we've already seen. However, I want to come back to Galileo in the end and show him to be a good guy too, all right? But for the moment, let us note that for him, mathematics meant geometry, indeed classical Euclidean geometry. And he is certainly emphatic. Without knowing that geometry, you can't read a single word in the book of nature. That does seem to be excessive. Still, We'll come back to him as a good guy. Now here is Stephen Wolfram, and here is the first statement about how mathematics can be superseded, complemented, augmented, replaced, various possibilities by other procedures which require more visual intuition. This and many subsequent quotes are taken from an excellent thing online, Quick Takes on Some Ideas and Discoveries in a New Kind of Science, written by Wolfram. His book, 846 pages with 300 pages of fine print footnotes, is perhaps complex, but he knows the relation of simplicity to complexity, and on his various website pages, he'll give you the whole book in one single page summary, and he'll give you quick takes. Here's a quick take. He will make the very quick take and then explain it. Mathematical equations do not capture many of nature's most essential mechanisms. For more than 3 centuries, we're talking Galileo to now, mathematical equations and methods such as calculus have been taken as the foundation for the exact sciences. There have been many profound successes, but a great many important and obvious phenomena in nature remain unexplained, especially ones where more complex forms or behavior are observed. Now, 2 other familiar faces, more familiar than Wolfram's perhaps. Talbott and Thornhill weighing in on mathematics. Astrophysicists are not trained in electrodynamics or plasma discharge phenomena. Such things would render their gravitational models obsolete. They continue to rely on gas and magnetized fluid physics that is mathematically well-mannered. Uncritical application of mathematical models will lead to whimsical and unstable descriptions of nature. So, Wolfram's exposition of his use of cellular automata and his claim that through them we can also study similar phenomena in nature is what I will now explore in the most technical part of my presentation. So, here is a cellular automaton, and here is the progression of it, and I'm going to explain both images carefully. But first, the quote, "Cellular automata are examples of simple programs that work by having the color of each cell in successive rows be determined by the same simple rule." So let's see the example. Here is the second cell in a checkerboard like this, in which the top line is, as it were, the initial state, and each line lower down is a subsequent state of evolution of the cellular automaton. The evolution is contingent on the rules for each of these 8 boxes. Let's look at this one. If the cell, the central cell, is white and flanked by both whites, left and right, then in the next stage it will be white. If white but flanked by white on the left and black on the right, then black, and so forth with each of these evolutions. Now, Wolfram took 255 cellular automata of this kind. All of them have rules exactly as simple as each other, and they lead to very different kinds of developments as you go from stage to stage, from horizontal level to horizontal level down the checkerboard. With the rules above, a simple pattern is produced. Here is the simple pattern evolving by these rules. Based on Chapter 2, The Crucial Experiment in a New Kind of Science, these images of cellular automata illustrate some of the core discoveries of NKS. And I add the 2 images above are Rule 90 in Wolfram's set of 255 rules. I hope you fasten your seatbelt, because if this page is unclear, it will only get more complex, all right? But we perhaps will have time for questions. Rule 90 produces an intricate yet ultimately regular pattern. Look at this. Isn't that lovely? It's a pattern. It's in fact fractal too, the beauty of fractals. That's Rule 90. A different rule, just as simple, producing a different pattern, which is getting on the left striated into bands, and on the right complex, bewildering. Wolfram has discovered and argues in A New Kind of Science that certain simple rules can produce patterns in behavior of immense complexity. Above is Rule 30. It soon becomes complex above, and at 100 steps it appears very complex indeed below. Can you see how striated bands are here, but this is rather random, isn't it? Well, it only gets worse if for you randomness is bad. At 1,000 steps, Rule 30, pardon typo, appears to have patterns in the bands on the left and to be random to the right of those bands. If one started with only one step 1,000, here, one could not reconstruct the simple rule that generated it. One would not guess that the rule was simple. And to look ahead to the grand thesis, suppose that this whole evolution is like some phenomenon in nature which you observe part of. So say you observe only this part, like there, that's all you can see. Would you ever be able to reconstruct the simple rule that generated it? Would you be able to guess that the rules that generated it were simple? Rule 10 is in a different category of rules from those generating either pandoms or randomness. There's Rule 110. As it evolves, a complex pattern emerges on the right and continues to morph into similar patterns at different shapes, none quite the same as the pattern preceding it. A mysterious statement which I'm about to illustrate. Here is its elementary rule, 110. Here is the opening sequence of steps. So far, it's just not so clear what's going to happen, is it? But this is the image I began with and asked you to hold that image. Rule 10 at 250 steps. I would gladly have given you it at 1,000 steps, but it seemed a bit too much memory. So, we have the patterning of striations. We have here something that seems to be monochrome, one of the possibilities. He sorted cellular automata when he was a boy wonder in his 20s into 4 categories. When they turn when they turn monochrome, when they turn patterned, when they turn random, and when they turn what he calls complex. This evolution is visibly something that in which each phase of it resembles earlier phases, but is not the same. It's what I call the Canadian phenomenon. You look similar, but somehow different. So, can you see that our eye sees this as a pattern? Our eye sees this as a pattern. This pattern resembles that, but is neither the same scale nor precisely the same shape. So we could watch this unfold a long time, perhaps forever, and would still not be able to predict the patterns in advance. That is the essential point of his take on the word complexity. Now, we've gotten through the worst and most technical part. What I shall now do is juxtapose statements from A New Kind of Science, taking Stephen Wolfram as a case among many fine laborers in complexity theory. I don't want to make him the sole star. That's been a problem with his reception, and I'm not interested in that problem. But many complexity theory people would make similar statements. Likewise, I'm going to take Talbott and Thornhill as representative of many fine workers and quite distinctive in their own contribution. And I'm going to juxtapose statements on a few topics: mathematics, complexity, and time. So you can see how they might be powerful natural allies, because there are similar views on these topics and others. Views on mathematics from the new kind of science. Thinking in terms of programs rather than equations opens up a new kind of science. Mathematical equations correspond to particular kinds of rules. Computer programs can embody far more general rules. The electric universe. Uncritical application of mathematical models will lead to whimsical and unstable descriptions of nature, a quote you heard from me before. All right. Views on complexity. New kind of science. Even extremely simple programs can produce behavior of immense complexity. That's what we saw in Rule 110. Everyday experience tends to make one think that it is difficult to get complex behavior, and that to do so requires complicated underlying rules. The discovery now that simple programs can produce immense complexity forces a major shift in scientific intuition. I love his choice of that word. By the way, it's from the Latin tueor, which means to look at. Intuition is just looking deeply at, all right? Electric universe. Although plasma behavior follows simpler electromagnetic laws, the resulting complexity continues to astonish the specialists who study it. Plasma can self-organize into cells of differing electrical characteristics. I included that last sentence because self-organizing is another term in complexity theory, which came naturally to the pen of the authors of Electric Universe. It's part of the language we now speak, really. Views on time, the third of the three topics I'm mentioning, new kind of science. Time may have a fundamentally different nature from space. The standard mathematical formulation of relativity theory suggests that, despite our everyday impression, time should be viewed as a fourth dimension, much like space. A new kind of science suggests, however, that time as we perceive it may instead emerge from an underlying process that makes it quite different from space. Electric universe. Einstein redefined Newtonian gravity by placing it in a metaphysical framework. He combined the three measurable physical dimensions of space with the mathematical dimension that cannot be measured by a ruler, time. The claimed success of Einstein's thought experiments encouraged mathematicians to follow his lead, and they have dominated physics and cosmology ever since. This skeptical attitude towards what Einstein did will, I take it, warm the heart of all who attend Natural Philosophy Alliance meetings. We're going to really relax because I'm going to tell you stories, all right? To prepare the ground, here is the last sentence of A New Kind of Science, and a quote from a poet placed by the authors of The Electric Universe at the top of the second page of that book. Last sentence of A New Kind of Science. All the wonders of the universe can in effect be captured by simple rules, but there can be no way to know all the consequences of these rules except, in effect, just to watch and see how they unfold. Tueor, to watch and see. Quote on second page of The Electric Universe, a quote I deeply love. The universe is made of stories, not of atoms. Muriel Rukeyser. By the way, I have another quote, and I think it's Whitehead, who was cited earlier. The event is the unit of things real. If that's not by Whitehead, please correct me, but it's a philosopher saying what a poet says here. Now I'm going to tell you an unpredictable story. One of the great serendipitous moments in the history of science, I like to think. Peratt's Christmas tree meets Talbott's chain of arrows. Chain of arrows. All right. This is the story. Some of you may have heard it in a simplified version. I am privileged to have received it from the horse's mouth, Dave Talbott, in an email of this week earlier. And I asked him to tell me the story of Peratt at a meeting where he said, "What are those?" And Talbott said, "Petroglyphs." And the first version I heard of it was, Peratt thought, well, these are my plasma shapes. What are they doing up there in petroglyphs? But here's Dave's telling of the story. We had invited Tony to our conference in September 2000. At a gathering of speakers the next day after the conference, Tony was inspired to go to the whiteboard and to draw some plasma images. Let's go back. There's the whiteboard. There are the plasma images. Then he drew out the chain of arrows, which he called the Christmas tree, upper left form in the attached. I said, "Tony, you've just drawn the chain of arrows, an image I directed Wall's attention to only a few days before the conference." Tony asked how the form evolved. I told him it began with twin filaments up the polar axis, dividing into a stack of embedded cones that emerged eventually as a stack of toruses called the ladder of heaven and backbone of the sky. Tony said that's how the Peratt instability evolved, the name given to the configuration by his co-workers. When he returned home, he asked me for the rock art images. And the first image I sent him was the Kayenta petroglyph, because I had no doubt he would recognize it. That was the squatter man from Kayenta, Arizona, really just across the border in northern Arizona from northern New Mexico. The moment Tony saw it, his life was changed. He had no doubt whatsoever that it was an intense plasma instability, and he immediately identified the parts for me. Dave attached this picture too. You can call these Christmas trees, arrows, or cones. They are either going up to or coming down from a red disk. That would be Mars. Then his attention immediately shifted to cataloging rock art images. And on numerous occasions afterwards, Tony confirmed to me that he had absolutely confirmed the formations I'd reconstructed, saying that he could also demonstrate conclusively in due course that they involved planets as the anodes and cathodes in the discharge configuration. That's the end of the story as Dave Talbott emailed it to me, entitling it "The Story in a Nutshell." So now the story takes on a dramatic global life. Peratt assembles a team to look at rock art all around the world and to put a GPS on each to see where it's pointing. Well, on that team is Marinus Antony von der Sluis, aka Renz. There he is with the Great Pyramids as backdrop. There he is in Mongolia. So, what does the team come up with? Well, I'm going to give you 3 examples of rock art juxtaposed to photographs by Tony. I think we're doing well on time because I'm coming to an end. And which will be familiar to many of you. And this is just to confirm that this global wandering team did indeed find rock art images corresponding to what you'll see as photographs, three-dimensional, of Tony's figures generated in a lab, and then a schematic drawing of them. And there again, we saw this at the beginning. This is the Kayenta petroglyph, which Dave first sent to Tony. So that would be the squatter man. I'm going to show you two more, and Tony, in his written work, says he has a total of 84 such plasma shapes in rock art. So a second would be, first, the schematic diagram of a stacked torus, and second, that image 4 miles west of here in Petroglyph National Monument, Rinconada. Support your local petroglyph. So 1, 2, 3, 4, 5, 6 stacks. 1, 2, 3, 4, 5, 6. Sometimes they're 5, sometimes they're more. 6 is very common. And we needn't go into the details of the schematic diagram. You've seen it before, you'll probably see it again. Finally, defining image for the tipping point. The Vajra, the Hindu word for the great thunderbolt which Indra wields, and which one fine recent translator, Stanley Lombardo, used in his translation of Hesiod's Theogony for the great thunderbolt which Zeus wields. Here is the three-dimensional photograph in Peratt's lab. Here is the tridental shape at both ends of the thunderbolt or of the trident of Poseidon. And here is the hand that grasps it of a god. My own specialty is Pindar, and in a poem, a victory ode for a young boxer from southern Italy, whose town had a lightning bolt on its coins, Pindar alludes to that coinage at the climax of the poem by speaking of Zeus's primeval victory, the pattern for all Olympic victories, where he overcame the Titans and Typhon with the bolt, as he says, grasped by the hand of fire. That is the hand of fire. The problem now for us is that Tony's story is about things that appeared in the sky that are not there now. The story is not finished until we can say how they disappeared, how they, as we might say, disintegrated, how, amping up the language, it collapsed catastrophically. That is the story Rentz has set himself to tell, and he does so purely through the language of myths around the world in the fourth of the 4 volumes of his recently published magnum opus, Traditional Cosmology, the Global Mythology of Creation and Destruction. Volume 4 is entitled, pardon the typo, Disintegration, and its subsections are disruption, disconnection, dispersion, inversion, departure, periodization, and eschaton, the last thing. So you can read that volume right now. So we return to Galileo. This is my last slide. And here Galileo is showing the Doge of Venice, his telescope. Too bad the Doge didn't use his power to keep Galileo out of the hands of the forces of the Pope and ultimately of lifelong house arrest. I'm going to summarize with 2 more quotes from A New Kind of Science. Simple computer experiments reveal a vast world of new phenomena. In their times, Wolfram goes on, telescopes revealed vast worlds that had never been seen before. Through the ideas of a new kind of science, computer experiments now also reveal a vast new world, in many ways more diverse and surprising even than the world seen in astronomy. And this from Thunderbolt of the Gods. The new data Galileo Great, we have lots of time. The new data Galileo collected in his first few weeks of telescopic observation overthrew the Ptolemaic view of the universe, a view accepted for more than 1,000 years. So I'm going to conclude with an anecdote from 3 weeks ago, at Bard College where I teach, and where I'm delighted to say all of the 500 freshmen in our freshman seminar are required to read not only Plato and Shakespeare, Dante and Virgil, but Galileo as the last reading. And it suddenly occurred to me in class as a way of saying that what Galileo saw and did with what he saw can be compared to something happening in the world today. And I chose Tony Peratt as an example. Galileo, I told them, made his telescope, looked through it, saw the imperfect surface of the moon, its valleys, its mountains, its ruggedness, and was compelled to tell the world of what he saw, and in so doing to overthrow the assumption by which the Western world had lived for almost 2,000 years, given it by Aristotle, consolidated by Ptolemy, namely that the moon and everything above it, the planets and the starry sphere, are perfect. They can have no irregularities either of motion or of surface. That worldview had to be overthrown. Galileo had to tell people that any of them, the Doge of Venice or you, can look through that telescope and see the imperfections of the surface of the moon. Likewise, Stephen Wolfram felt he needed to tell the world, after looking at Rule 110, that that highly complex behavior, so complex that its continued evolution cannot be predicted, it just has to be watched unfolding, can be generated on a computer in cellular automata, and you can see by the mode of its generation that complexity came from very simple rules against all our intuition. Finally, Tony Peratt saw in his lab the shapes that kept morphing from one to another as he added more current. Then he saw those rock art forms, as Wall had seen from Dave 6 years earlier, and was compelled to tell the world, all three of them, that the sky that ancient man and woman saw, the ancient sky, was not the same as we see today. That is overthrowing a still dominant assumption. And the seers of those plasma shapes and petroglyphs have felt compelled to tell the world it was not so. The ancient sky was different. Thank you.